All right. So, hi everyone. I am Ritojit Kundu, a PhD scholar at IIT Kanpur. So, I am one of the TAs in this course of Advanced Quantum Mechanics with applications. So, today we'll be talking about week 8's contents. So, mostly I'll be talking about some time-dependent problems. So, where the Hamiltonian has explicit time dependence, and so we'll see. We'll solve some problems so that you can also in turn solve week 8's assignments. Okay, so first of all, let me check with everyone. Is my audio clear and can you see my screen also? Can anybody confirm? All right. Uh, so let us begin. So, okay, so let's do this one. So, at t less than 0, so this is a problem one, and t less than 0, the particle that we're talking about is in the ground state of a infinite well. So now the first problem is if the wall is moved slowly to some other distance. So initially it was going from 0 to A. So wall was from 0 to A. Now after shifting the wall, it becomes 0 to 8A. So the question is what is the energy of the final what is the energy of the particle after doing this operation, and what is the work done during this process. Okay, so you see there is a time dependence in the Hamiltonian because I am shifting the walls, right? So here we have to be careful about what is this thing slowly means. Okay, so whether this is adiabatic or not, we have to first understand, and then we can actually write down the wave functions and energy pretty easy. So okay, so first of all, let's see what is slow or what is fast. So in any quantum process, so there is we say there is a time scale. So you see that so in the energy, so the energy always appears something like in a way something like this. So e to the power some ei times t by h bar. Okay, and generally I have many states. Okay, so let's say this is 1, this is 2, 3, and so on and so forth. Okay, and so this energy difference actually gives me one time scale. So what is that? So E2 minus E1 times t by h bar is actually so yeah, so this you can say, okay, this is of the order of 1. So let's say this is of the order of, so we just want to get the scale. So we want to find what is the time so that the transition happens between these two states. So this time is actually given by h bar by E2 minus E1. So this is the typical time so that a transition can happen between, let's say, state 1 and state 2. Okay, so by slow we mean that our time scale, let's say our time scale of shifting the walls is t, is actually much larger than this t. Okay, so that means this t is actually much larger than h bar by E2 minus E1. So that only then we'll call it slow. Okay, so that means we'll be able to use adiabatic approximation. Okay, so this is the meaning of slow. Okay, so just to qualitatively understand what is happening, right? So now if the way we are shifting the walls satisfies this condition, like when initially there was the system was between 0 and a, the walls were between 0 and a, and then after time t the walls are now at 0 and 8a. Okay, so this t is actually much larger than this energy scale, so that the transition can happen. Okay, so this is the meaning of slowness. So now if that is the case, so what will happen? So initially my wave function is actually in a ground state. So the particle is in the ground state in this potential well between 0 and a. Okay, and if this change is very slow, right, so then actually what happens is, as you are increasing the length little by little, it will always follow the ground state of the new system. So this is some 0, 0 to 2a, and let's see we're increasing this wall slowly, right? So it always follows the this ground state of the new system. Okay, so let's say now after a long time it becomes 0 to 8a, then also it follows the ground state. Okay, so this is the meaning of the adiabatic approximation. So all of the changes are very slow, so that the initial state, I mean that it follows the spontaneous ground state. So now if this is the case, so we know the initial state. So let me write it as psi I. So psi I stand for initial state. So initial state was the ground state of the potential well between this, right? So we know what is the wave function of that. So the wave function of that is given by 2 by a square root sine pi x by a. Okay, so this is my initial state. But after time t, my final state is actually a ground state of the large potential well, which is between 0 and 8a. So now it becomes 2 by 8a square root sine pi x by 8a. Okay, so this is the ground state of the final potential well. Okay, so this is all right. Okay, so now the question is, what is the work done to do this change? Okay, so how do we do that? So we know initially, so the energy corresponding to this state is given by so n square pi square h bar square by 2 m a square, right? So here n is 1. So the energy was this. Okay, so let me also mention an I index, and energy of the final state is given by, so also 1 times pi square h bar square and 2 m. So instead of a we'll be using 8a here. Okay, so that makes it 128 m a square. Okay, so now we see that, okay, there is an energy difference. Okay, so what is the work done? So work done is let me write it. Work done between initial and final to make the final system is given by EF1 minus EI1. Okay, so you go on and calculate this square by 2m a square, and so in the downstairs I will have 61 by 64 minus 1. Okay, so this is the amount of work done that we need to do do this kind of change. Okay, so this is the idea of adiabatic changes, right? So that actually completes the part 1. So is that okay? Any question, any confusions? Okay, so now we have done this thing slowly. Now there is the other limit when we'll be moving this walls suddenly. Okay, and we'll be asking some questions that, okay, what is the probability of finding the particle in the ground state, and what is the probability of finding the particle in the excited state? Okay, so let's see how to do that. So initially my system was 0 to a, and the particle was in the ground state of the potential well, right? And then at t is equal to 0 I did a sudden change. So sudden change, after doing that, the well become actually wide enough, but because this is not adiabatic, it is not following the ground state of the new system, of the new potential well, right? So even here also our state is like this. Okay, so it is only the initial state. So the meaning of this is that psi I of x, so I stands for initial, of x was the ground state of the initial this well. So it is given by 2 by a square root sine pi x by a. Okay, so so this is when the x is between 0 and a. Okay, and else it is 0. So when x is greater than a, this is 0. So this is a piecewise function. So now we clearly see that this is not a ground state of the new system. So now the question is, okay, so what is the probability of finding the particle in the ground state of the new system? Okay, so just to make this a little bit more clear, so the ground state of the new particle, this new system is something like this, right? So that means and the other theorem that you know from quantum mechanics, that any wave function, so any wave function you can expand in terms of the eigenstates of our system, right? So psi n x cn, okay, and this cn mod square tells you what is the probability that the particle is found on that particular nth state, right? So yeah, so now what we want to find is our new states, first of all, is given by 2 by 8a sine pi x by 8a. Okay, so okay, so let me also mention the n quantum number. So this is n pi x by 8a, right? Now what I want to find is, I want to find different cn's. So cn is given by psi f n x star psi I x dx, or the integration goes from 0 to a, okay, 0 to 8 actually. So this is, I am calculating the overlap, right? So I'll have to calculate cn mod square to see what is the probability, right? So is this clear what we are trying to do here? So this is our state at psi 0, and we are trying to find out different coefficients so that we can find out what are the probability of finding this particle in each of these states. So let us do this integration. So, and we see that this wave function is just non-zero between the 0 to a, okay, and on the other parts of the potential well, it is actually 0. So that makes our life a little easier, and so that then we can also replace the limits by 0 to a psi f in x star and psi I x dx plus a to 8a psi f in x star and psi I x dx, okay, and between this psi is actually 0, so we are only left with 0 to a psi f in x star, and there is psi I. So psi I is given by 2 by square root a sine pi x by a. So this is the integration we have to perform. So, and let's also write the psi f n. So this is 2 by 8a square root and sine n pi x by 8a. Okay. So let's take few of these things common. So it becomes 2 by a so square root 4 by 8 a square. So there is, it is just 1 by square root 2, 1 by square root 2 a, 0 to a sine n pi x by 8a sine pi x by a. So let us also do a change of variable so that the limits become a little easier to handle. So we'll be using pi x by a as a new variable. Okay, so if that is the case, then our dx becomes a by pi dy, and the limits, so let's look at the limits of this new variable. So x and y, so x was 0 to a, so that makes y 0 to pi. Okay, so let's do this change of variable. y by 8 sine y. Okay, so now let's do this integration. So let's just focus on this integration. So the a actually cancels from top and bottom, so we are just left with this thing, and this is just a number. So let me write this as I. So I is the integration of value of this integration. So now let's focus on this I. So here we can use the trigonometric identity, which is given by sine of a times sine of b is given by cosine of a minus b minus cosine of a plus b by 2. Okay, so now that makes this whole expression, so it becomes cosine of n y by 8 minus y, and there is minus cosine of n y by 8 plus y. Okay, and there is 1/2 outside. So now it becomes easier, so we have to just do two cosine integrations. So this becomes cosine of n y, so it becomes n minus 8 by 8 times y, and it becomes cosine of n plus 8 by 8 times y. So cosine integrations are pretty easy, right? So you just, it becomes just sine of n minus 8 by 8y by n minus 8 by 8, and you put the limits 0 to pi, and there is additional minus. Okay, and there is also sine n plus 8 by 8 y by n plus 8 by 8. Okay, no dy here, just 0 to pi. Okay, so okay, I think I have probably done some mistake here, or no, this is fine. So half minus sine, so it becomes n minus 8 by 8 pi, and on the downstairs we also have n minus 8 by 8. Okay, and the 0, when you put 0 in this place, the sine 0 is 0, so we just don't care about that term, and then it becomes sine of n plus 8 by 8 pi, and on the downstairs it becomes n plus 8 by 8. Okay, so this is just plain simple algebra. So let's write the final form. Sine n by 8 plus 1 times pi divided by n by 8 plus 1 minus sine n minus n by 8 minus 1 pi, and divided by n by 8 minus 1. Okay, so this is the final form. So this is your I, and this Cn depends on, so see, I has actually n index, so it depends on which state we're talking about. So let's better write it as In. So here also I will write it as In. So Cn is nothing but 1 by square root 2 pi and some In. Okay, and you then calculate the mod square, and you are done with this. So you know what is the probability of finding that particle in the nth state. 1 by 2 pi square In square. Okay, so you go on and plug in some numbers. Some n is equal to 1, which is the ground state, 2, which is the first excited, and try to see what is the probability. What is the probability in terms of numbers? Okay, you go ahead and do that in your calculator. So this is the result we have been looking for. Okay, so is this clear? Any questions? So all right, so let us move on to the next problem. So now this is a problem about time dependent perturbation theory. So we'll be calculating some probabilities, okay, of transition probabilities up to first order, right? So because then after first order it becomes a little bit complicated, so there will be two time integrations which we'll have to do. So just for simplicity and get the idea of how to do this kind of calculations, let us focus on this first order correction. Okay, so here what we are looking at is, so a particle at t when was minus infinity, so that means in far past, is in the ground state of an infinite potential well. All right, now we apply a small time dependent perturbation. So here the small again, smallness means that it is much smaller than the energy differences between two consecutive states, let's say. So it is much smaller than that energy difference. So this is the perturbation, this is the time dependent perturbation. So epsilon here is a small parameter. So now we are asking what is the probability that the particle would be found in the first excited state at far future. Okay, so this is like a standard kind of problem in the time dependent perturbation theory, and from the lectures of week 8 you probably are aware that this is the first order correction, first order in transition probability. Okay, so this is what we are interested in, and let us see how to do this sort of calculation. Yeah, and here also we'll be using this similar kind of identity. So in all of these problems of particle in a box, this identity is actually useful, so you can just keep this formula handy. Now, so what you have to do is, so our psi I was psi I at x of x at t is minus infinity, but we don't have to mention the t argument also. So psi I x was a ground state. Okay, and the final state is the first excited state of the same potential well. Okay, and so let's first try to calculate this part. Okay, so this is my psi j vt psi I, which is, when you write in terms of integration, this becomes 0 to a psi f of x conjugate, so vt, let me just use a form of vt which is x operator minus t square, and then I will have psi ix. Okay, so this is the first term that that we would like to calculate. So let's put all of the forms here. So it is 2 by a sine 2 pi x by a x sine pi x by a, and I am taking the epsilon out. Okay, so now here again we will do the similar kind of change of variable that you have done before. So the reason of doing that is it actually extract all of the parameters out of this integration. Okay, so in many cases you can go away and get away with just changing this variable, and you can look at a lot of physics, and you don't have to evaluate the integration also. The integration is just a number. So that's why this kind of change of variable is actually important. So here we'll be taking our pi x by a as y. So that will make our dx a by pi dy. So in the limits of this new variable will become 0 to pi. So let us replace this new variable. So sine 2y ay by pi sine y, and dx will be changed by a by pi and dy epsilon 2 by a by pi whole square. So here so let's call this integration. So this is just a number, it doesn't depend on any parameter, so all of the variables inside the integration are dimensionless. So we'll call this integration as some I. Let's first calculate the I. So to calculate the I, we'll be needing that trigonometric identity, and also we'll have to use integration by parts. So let's put that integration identity. So cosine of 2y minus y minus cosine of 2y plus y. Okay, so y times cosine of y and minus cosine of 3y. So this is the integration that we have to do. Okay, so you see that there are integrations which are just like y times some cosine of y, and there is also the just number which is sitting here. So just to calculate both of these terms at once, so let us calculate this. Let us calculate y cos ny. So for the first term we'll be setting n as 1, and for the second term we'll be setting n as 3. So you have to do integration by parts. So the way I'd like to do this is just make this cosine as a derivative of sine ny and divided by n. Okay, so that you again get back cosine. So when you are done, when you are written like this, the integration by parts becomes really simple. So you see that the first term is actually this actually is 0. Okay, and the second term will give us cosine of ny, and this minus will get cancelled, so it will become n square 0 to pi. So this becomes cosine of n pi minus 1 by n square. So cosine of n pi for any integer values, it is just minus 1 to the power n. So we see that if okay, so this has two cases. So n is even. So if n is even, so then this integration is 0, and if n is odd, then we get 2 minus 2 by n square. Okay, so let us use this thing and calculate this quantity. So now this is half. So the first term, so n is actually odd, n is 1 in this case, so we'll just put minus 2 by 1 square, right? And the next term is also, there is additional minus, so it will make it plus. So then I'll have 2 by 9. Okay, so 3 square, it makes it 9. So what do we have? So let us just calculate this this integration. So it becomes, so this is just minus 2 plus 2 by 9 half minus 18 plus 2 by 9. So it is minus 16 by 2 times 9. It becomes minus 8 by 9. Okay, so now we can actually plug this back here. So it becomes epsilon by so 2 epsilon times a by pi square times minus 8 minus 8 by 9. Okay, so this is the whole answer of this first part. So this only this part. Okay, so now there is still a time integration which we are yet to do. Okay, so I have actually missed this factor. So the e to the minus t square is always there. E to the minus t square is throughout there. Square to the minus t square. Yeah. So now let us do the time integration. So the time integration, if you look carefully, it is given by e to the power minus t square, right? And there is also e to the power I omega 21 t. So omega 21 here is given by the energy difference between the first excited state and the ground state. So which becomes 2 square minus 1 n square pi square, okay, not n square, pi square h bar square to m a square. So it makes it 3 pi square h bar square to m a square. But let's call this quantity omega for now. So there is omega sitting here, and the integration limit is between minus infinity to plus infinity. So this is the t integration part. So the way to do this integration is to complete the square in the exponent. So in the exponent, if we combine all of the terms, we have minus t square minus I omega t. Yeah. Okay. So yeah, that's correct. So if that is the case, so we can first try to complete this square. So t square minus I omega t becomes t square minus 2 times t times I omega by 2. So I'll just add this I omega by 2 and subtract this I omega by 2. So this becomes t minus I omega by 2 whole square minus so minus and minus plus the omega square by 4. So again, let's put all of these things back in the exponent. Minus infinity to infinity, e to the power minus t minus I omega by 2 whole square, and then there is additionally minus e to the power minus omega square by 4. Okay, so this is the whole quantity, and you know that, so you know from Gaussian integrations that this first quantity is just square root pi. All right, so now we have all of the components. So we have this part, okay, and we also have this time integration. Okay, so now you can just combine this thing and this thing, and you take a mod square, and that's it. So let me just assemble all of those parts. So let me take this one. So this P21 is given by 1 by h bar square, and there is mod square of this quantity times e to the power uh, uh, anybody has any question? Okay, so let us continue. It is minus omega square by 4 mod square, right? So this is the P21, and you just do some simple simplifications. It becomes, so 4 times 8, okay, so so this is 2 epsilon a by pi square 8 by 9 whole square of this thing, and e to the minus omega square by 2. So this is your transition probability up to first order. So this is the first order. Okay, so is this okay? So we calculated each of the terms, each of the parts separately to avoid any kind of mistakes, and we just assembled all of the parts. So is this okay? Any questions? All right, so if not, so let us do another similar kind of question, but for a harmonic oscillator. Okay, so this is similar to the previous problem, but here we'll not have to do this kind of integrations because we'll be using operator algebras, okay, which are much more cleaner than those kind of integration by parts. So in this case we are given a field time. This is a v0 is a small field, and there is this time dependence, okay, and x cube is actually sitting here. So initially the particle is in the ground state. Okay, now the question is we have to find the transition probability to the nth excited state. Okay, so let me actually copy that formula from beforehand, and we'll be again doing the similar way. So let us first look into this part. Okay, so you want to calculate in v is a function of x and t and 0. Okay, so this is a quantity you want to look at. So v has 3 parts. So v has some constant and x cube operator and e to the minus t by tau. So let us first look into this quantity in x cube and 0. So you know from basic quantum mechanics that this x is, it can be written in terms of the ladder operators, creation and annihilation operators. So let us just use that in, and so let us first write x cube. Okay, x cube is just a plus a dagger plus a times a dagger plus a times a dagger plus a. Okay, so let me write the matrix element. Okay, so there is n sitting here and there is 0. Okay, so whenever we are dealing with operators, so we should not actually use formulas like this, a plus b whole cube, like this kind of formulas. The reason is these formulas are mainly for things which commute. So like the numbers, real number or complex number, they commute with each other. Okay, but when we are dealing with operators, then it becomes a little tricky. So the best way is to expand this manually, okay, without using any formulas, to avoid any kind of mistakes. So now it becomes, so let us do part by part multiplication. So a dagger square, so I'll be multiplying these two first. So a dagger square plus a dagger times a plus a dagger plus a square. Now let's complete the last multiplication. It becomes a plus a dagger square. Okay, so it becomes a dagger cube plus a dagger a dagger plus a dagger square plus a square a dagger, and there will be additionally a plus square times a plus a square a dagger a plus uh, a cube. Okay, since the whole thing is so we are taking a matrix element between the n and 0. So from here we can actually see most of the things becomes 0. So which are the things? So any a to the power n, when it acts on the 0, so a is the annihilation operator, and there is no state lower than 0, so it makes it 0. Okay, so with that we following that reason, this quantity will become 0, this will become 0, this becomes 0, this becomes 0. So the reason here is just that this actually has the a on the right. Okay, that's why all of these terms are 0. But if you look at the other terms, you will see that there are no there are no annihilation operators on the right. Okay, so this will not be 0. Okay, so we'll have to calculate this only. So let us just copy these parts. So okay, so now you have to calculate all of these matrix elements. So for example, n a dagger cube 0. So what is this? So let us act one by one of these a's. So n times n plus square, it becomes 1. A plus square, okay, so then I'll act another n, so it becomes a dagger square root 2. Okay, so this 2 square root 2 is for the normalization. So then I'll act another a dagger. Now it will become n square root 3 factorial and 3. Okay, so n 3 factorial is just a number, so I'll take that out, and so I'll have n comma 3, and all of these states are orthogonal, right? So now it becomes delta n3. So this is just the Kronecker product. This is a Kronecker delta. So similarly, you can find all other combinations of this thing. So a dagger, a and a dagger. So a dagger will increase it by 1 and a will decrease it by 1. So nothing will happen. So we'll only have n a dagger 0. Okay. So then it becomes n and 1. So then it becomes delta n 1, Kronecker delta n and 1. Similarly, you can calculate the rest of the two terms. Okay, so now when you are done with that calculation, so we have done this part, right? So now there is one part remaining, which is doing the integration of this quantity, right? So omega in this case is just omega n and 0. So omega n and 0 will be omega of n minus omega of 0. So n plus half h bar omega minus half h bar omega. So it becomes just n h bar omega. Okay, so this is the omega gi in our case. So now the time integration part. So let us just look into it. So the time integration part is so 0. Okay, so let us do it like the 0 to infinity and e to the power minus t by tau and e to the power minus I in omega. So this is the time integration that you have to do now, in omega t dt. So let us again combine all of these terms in the exponents. So it becomes t times 1 by tau plus I in and omega. dt. So now you can do the integration of the exponentials. So it becomes e to the power minus t 1 by tau plus I in omega divided by 1 by tau plus I in omega, and there is an additional minus, and you have to take the limit between 0 to infinity. So what happens is, at the infinity limit, because of this part, this whole quantity becomes 0. Okay, so only term which will remain is just the 0 term, which will be given by so 0 by 1 by tau minus I in omega. Okay, so this is the result of the integration. So now you have to combine all of the parts, right? So now you go ahead and complete these two integrations, I mean two matrix elements, and you plug this thing into the formula of this transition probability, and you are good to go. You can find any transition probabilities between the ground state and the nth state, okay, up to first order. So this calculation is only up to first order. For second order, there will be another time integration also, okay, which is also straightforward, but that needs a little more algebra. So is this okay? Any questions? Okay, so if not, let us move on. So the point I'm trying to make here is, like, the problems which you will probably see in this time dependent perturbation theory is mostly like this. So you'll be given some system, particle in a box or harmonic oscillator or hydrogen atom, and there will be very small time dependent field, and you will calculate first order and let's say second order in transition probability. Okay, so this is the task. Okay, so this is, I mean, this is a standard problem of time dependent perturbation theory. So now the one other thing that I want to talk about is actually a really interesting topic. It is called the Berry phase. Okay, so I'll be not covering the full topic of Berry phase, but I'll be giving a very small introduction in terms of some calculating some toy model. Okay, so what is this Berry phase? So Berry phase is actually a phase which you will obtain if you have time dependence in your Hamiltonian, or you have some periodicity in a Hamiltonian, and you are traversing a circle in some parameter space. Okay, it doesn't have to be time only, it can be some other quantities as well. So let's say the Berry phase, so this is one form of the Berry phase. So the Berry phase is given in terms of a long chain of inner products. Okay, so this might look very intimidating to you, but let us just break this down. So you see that, so like, let's say this is my path, okay, on some parameter space, and this path is discretized into some number of points. So I have n number of discretization on this path, and I have indexes 1, 2, 3, 4 and n minus 1, like that. And see, first look at this term, so u0 and u1. So what does it do? So it actually takes the inner product between these two states, okay, which are kind of close in a parameter space, which will take the inner product between these two states. So the next state, next term is u1 and u2, inner product between u1 and u2. So that will take the inner product between these two states, and u2, 3 will take inner product between these states. And if you go on and if you follow all of the terms in the sequence, you will see that this takes only the inner product between this individual between the nearby states. Okay, and at the end of the day, we are multiplying all of these things and we are taking a log. Okay, and then the imaginary part of this whole thing. So what is happening is, so like this whole quantity, so the whole quantity will be some complex number, right? Because these are inner products, these are just complex numbers, so it will be some z, right? So a complex number we can also represent in terms of a amplitude and the argument phi. Okay, and I want to find what is the argument. So if I want to find the argument, what I will do is I will take first log. So then it will give me two parts, log of r and plus log of I phi. Okay, so then if I take, okay, so log of e to the power I phi, so then I have log of z is equal to log of r plus I phi. So now if I take the imaginary part of this function, so that only gives me this phi. Okay, so it depends how you define this complex number, plus and minus, plus or minus, you will get a plus or minus here. Okay, so this is the idea. So what it does is, what this quantity does is, it accumulates all of the phase difference that you can have from during traversing the path. So it accumulates all of the phases and it will give you just the phase it gains during a cyclic evolution in some parameter space. So this is what Berry phase tells you. Now the Berry phase is particularly interesting into modern research, so because it is related to topological insulators, okay, and it is also important in quantum informations. So in all topological insulators, you will again calculate this quantity. You will find some non-trivial, some phase. Okay, so if a system, in a system you are calculating this quantity and you get the phase becomes 0, then that becomes a trivial kind of insulator. And if this becomes non-zero, it becomes a topological insulator. Okay, which is actually, I mean, you can look into that, but we'll not be going into that also. So let us say in some parameter space we have discretized this path, and you're calculating this quantity, which actually gives us the total phase which is accumulated by traversing the path. So this is what we refer to as the Berry phase. Okay, so for today's which problem we'll be working on, this definition is all right. We don't need anything more. So now let's do two examples. Okay, so now I have this states. So I have UA, UB and UC. So these three states corresponds to 3 points on a path. Okay, so this is my A, this is B and this is C, and I want to calculate the Berry phase when I am traversing through this path, okay, and coming back to A. So this is the quantity that I have to calculate. So now let's do this calculation. So to just get the idea, let me just copy this part. So now I'll have to calculate inner products between nearby links, right, nearby indices. So I'll calculate UA and UB, okay, UA and UB, so that I have this part. So first of all, let's just do that, UA and UB. So this is just 1 by square root 2, 1, 1, and there is 1 by square root coming from the other UB also. So I'll just keep it as 1 by 2, so e to the power 2 pi I by 3. Okay, so you go on and calculate this quantity. It becomes 1 plus to the power 2 pi I by 3. So this is the inner product for the first link, let's say. Now you have to calculate this B to C. So we'll be calculating UB and UC. So this becomes 1 by 2, 1 e to the power minus 2 pi I by 3 and 1 e to the power 4 pi I by 3. So if you do that, you get 1 plus e to the power 2 pi I by 3. Okay, so and the last term is this part C2A. So UC to UA, so I have to finish at A, right, because I have to complete the whole path. So this again becomes 1 by 2 e to the power I 1 e to the power minus 4 pi I by 3 and 1 and 1. Okay, 1 plus e to the power minus 4 pi I by 3. So now I have these three components. Okay, so I can plug this all of these things. So UA UB, UB, UC, UC and UA. So now let us write these things. So half 1 plus e to the power 2 pi I by 3 times, so there will be total 1 by 8 plus 1 plus e to the power 2 pi I by 3 times e to the power 4 pi 1 plus e to the power minus 4 pi I by 3. So let us compute these things. So it becomes 1 by 8, 1 plus, okay, so what is the e to the power 2 pi I by 3? We can just plug in those values also. So sine of 2 pi cos of 2 pi by 3 plus I sine 2 pi by 3. Okay, you can do what, but you know what, so keep it like that. That will make our life a little simpler. So 2 pi I by 3, yeah, plus e to the power 2 pi I by 3 plus e to the power 2 pi I by 4. Okay, so it becomes 4 pi I by 3. So now there is also this term 1 plus e to the power minus 4 pi I by 3. Okay, so you go on, you calculate this quantity, you so at the end what you will get is you will get so okay, so if you calculate this imaginary part after taking the log of this whole quantity, okay, which is the Berry phase, you will see that this becomes actually minus pi. So this is a little strange kind of thing, because what happens is, when you look at like normal daily objects and say we are moving a daily object from here some point to some point and some point to some point and some point to some point, okay, so now we know that it is the same object, right? So if I take a pen, I just rotate it once, it is still a pen, none of the property actually changes. But for wave functions, this can give rise to a phase which is a non-trivial phase, okay, which is not an arbitrary phase. So it depends on what is the geometry of the path. It doesn't depend on the energies of the system, it only depends what is the geometry of the path. So it is also called a geometric phase, okay, it only depends on geometry of the path. So this is one example of Berry phase, okay. So we can actually look into another example which is also very interesting. So this is called Berry phase on a Bloch sphere. So from your angular momentum, spin angular momentum sessions, you might be aware that we can write any state of a spin half particle as this, so which is a spinner, okay. So there is cos theta by 2 and sin theta by 2 sitting here, and the phi also is here. So this theta and phi sets the orientation of the spin, okay. So it tells you which direction is the spin is oriented. So now I am asking, so and also all of this state, if you plot them, so you will see that these are just arrows. So the length of these things are just like so these are like unit arrows, and the n cap will tell you in which direction the arrow is actually pointing. So you will be able to see that, okay, some n cap direction is pointing here, some n cap direction will be pointing here. So it will point on different points of a sphere, which is called a Bloch sphere, okay. So all of the states actually they live on the Bloch sphere for spin half particles. So they live on the Bloch sphere, and if we just change our position from one point to another point, we will go to one spin state to another spin state. For example, if our initial spin was pointing in the z direction, positive z direction, we will have a spin up half particle, spin up state, okay. But on the other hand, if we just look at the south pole, we will see that this is a minus half. It's in the minus half state. Okay. So now with all of that, what you want to do is when to calculate a Berry phase when we are rotating the spin. Okay. So what do I mean? So now let me try to draw a sphere. So this is the block sphere, and so this is the equator. Okay, and let me also try to draw the axis of these things. So this is Z, this is X, and this is Y. So now I want to rotate the spin in a way that it first starts from this position, then it goes to on the Y axis, let's say on the Y axis, and then it goes to the north pole, and it comes back to 0 again. Okay, so we want to start from here, and we want to come back to again this point. So that will give us a Berry phase, right? So to do that, you first have to put these different values of theta and phi to get these states. So let me show you how to do that for this case. So let's say initially my x-axis. So let's make a cleaner plot. X, Y, and Z, and this is r hat direction, this is theta, and the projection is phi. So the x, in the x direction, what we have is our phi is 0. Phi is 0 and theta is pi by 2. Okay, so actually from this figure only we could tell. So our phi has to be 0 to be on the x-axis, and we have to come back here. We have to set our theta as pi by 2. Okay, and now let's say I want to go to y-axis. So for y-axis, the phi is pi by 2, and this theta is also pi by 2. Okay, and for the z-axis, the coordinates are phi. Okay, so for the z-axis there is no meaning of phi actually, so because at that point that phi becomes undefined. So let's write as undefined, and theta is just 0. Okay, so you will see that okay, so let's first write the state x. Okay, so up x. So for up x, I'll plug in this theta and phi into that expression. Okay, so phi is 0 and theta is pi by 2, so it becomes cosine of pi by 4 and sine of pi by 4. So that's it for the up x state. So it becomes 1 by square root 2 and 1 1. So this is my x state. Similarly, I will find my y state. So for y state I'll plug in cos pi by 4 and sine pi by 4. Additionally, there will be e to the power I pi by 2. Okay, so this becomes 1 by square root 2 1 and it becomes I. Similarly, the z, for z you will just use theta to be 0. Okay, so for theta 0, the first component becomes 1, and in the second component sine theta is sitting there. So even if phi is undefined, we don't have to worry about that because sine theta takes care of it. So if you carefully look at these states, you will see that this is actually plus half eigenstate of sigma x, this is plus half eigenstate of sigma y, and this is plus half eigenstate of or not. Okay, so this is just plus, no half here, plus, and this is plus state of sigma z. Okay, so that's it. So now what we want to do is we want to calculate the Berry phase across the whole path. So this is, you see that this is the first octet. Okay, so this is one of the octet. Okay, so you go ahead and calculate this quantity. So up x, up y, up y, up z, up z, and up x. Okay, you take the log of this thing and take the imaginary part, minus of imaginary part, so that will give you the Berry phase. Okay, so and you will see that this quantity will give you pi by 4. Okay, so you see pi by 4 is not a random number, so that which came out of our calculation. This is actually the solid angle of the first octet, solid angle of this Bloch sphere of the first octet is just pi by 4. Okay, so it should be actually pi by 2. It should be pi by 2, not pi by 4. Okay, you can check this. Now you know that the whole so for a sphere the whole solid angle is actually 2 pi. Okay, and you will see that this so if you just okay, no, it should be actually pi by 4 only. Yeah, pi by 4. And you see that if you, so this is one octet's solid angle, right? So if you just multiply with 8 other octets of the sphere, you will see that this gives you 2 pi, which is the whole total solid angle of the sphere. Okay, so yeah, so this is like some calculations of Berry phase, some simple calculation of Berry phase. Okay, so this is also called Berry and Pancharatnam phase. Okay, just for your information. So is this okay? Any questions? All right, so this was the last problem that I had to talk about, and so if there is no question, so we can finish this session. Okay, so you will have the recording of this video so that you can watch later also, and the notes of this session, you will also have access to that notes also. Okay, so then if there is no other question, then let us finish this session, and I hope you have a good weekend. Okay, okay then.